we talked about how far apart the particles were in gases and in liquids. And in gases, we said small numbers of particles very, very far apart. In liquids, we said that they were a lot closer together, but just like dance partners, they were still free to move around one another, change partners, slide past one another, all that. When we get into the solids, now they are not only more closely packed, but they are locked in place. They're not allowed to dance. There's no dancing in the solid phase of matter. The particles are locked into rigid formations. Okay? And there are two big categories. One is crystalline and one is amorphous. And from your outlining yesterday, you should have a pretty good idea what that means. When we have a crystalline solid, the particles, the atoms, are locked in a very regular pattern which repeats itself.
They can actually move, though.
Well, they don't. They flex in some cases. I mean, you can flex those bonds, but they don't flow past one another. They don't change their position. The bonds get compressed or extended, but the molecules themselves don't change their position. So even if you can flex something, the atoms stay in the same places. Okay? So that's a crystalline solid. And what's really interesting is if you think back to our molecular geometry, we talked about ionic compounds and how we couldn't really draw the geometry for them. They're not covalently bonded, but they tend to get locked into position. And what you all have in your hand or on your desk is one of my favorite ionic solids. What is it? Sodium chloride. So it's made up of an equal number of sodium ions and chloride ions. And I'd like you to look real closely at that and see if there's anything you notice. Here's the amazing thing. So you've all got little chunks of rock salt on your desk, and we've got a picture here of some of the same salt that you have. That came from a salt mine underneath Lake Erie, about 2,000 feet down under Lake Erie, the Morton Salt Mines. If you ever get a chance to tour there, it's really cool. The walls are made of salt. And you can take a hammer. If you're on an educational tour, you get to take a bag and a hammer, and they'll take you to a section where you can chip off crystals. And so I've got a bag of salt that I brought home. Do you notice anything unusual about that salt? Okay, so the two things that I really wanted you to notice are that it tends to break along straight planes. It forms squares and angles when it breaks. The neat thing about crystalline solids is we can actually very often, from the shape of the mineral on the surface, we can see the orientation of the individual atoms within the substance, which is amazing. And they call this cleavage, and we talk about break planes if you get into minerals and geology. But sodium chloride forms nice, neat squares. It's a 1-to-1 ratio, and they form a 3-dimensional square grid, and that's reflected on the surface of the substance. There are a number of shapes that you can talk about with crystalline solids. Your book goes into cubic, tetragonal, hexagonal, monoclinic, triclinic, all of those. I'm not going to test you on those. Well, actually, we probably will have a small quiz, but not... Anyway, we'll talk about that later. When we go to the Carnegie Museum, you will see samples of all of those types of shape. Okay, so in contrast to the crystalline solids, we have what are called amorphous solids. And plastics are the classic example. So morph means shape. If you think about, shapeshifters morph into other things. A means without. And so something that is amorphous doesn't have a definite shape. There's no definite arrangement to the molecules in an amorphous solid. They're kind of all over the place. And plastics are like this. There are a few other examples, but that's really the classic. Okay, so if we talk about all solids, crystalline or amorphous, there are a couple things that are true. Definite shape and volume, you know that. And if we think about this in terms of kinetic molecular theory, They have a definite shape and volume because those molecules are locked into, molecules or atoms are locked into fixed positions. They can't move, they're rigid. They have definite melting points, and the melting point is where we go from being a solid to a liquid. The melting point is the point at which you've got enough thermal energy. Because remember, temperature is actually a measure of what? What other kind of energy? Kinetic. Kinetic molecular. So the melting point is the point at which you've got enough kinetic molecular activity to overcome those attractive forces, to overcome those bonds, and they start to flow. Solids are all high density. We said that. We talked about, gases, liquids, solids. Regular, fixed, and very high density. They're incompressible. You cannot compress a solid at all. Can't do it. If you think you are compressing a solid, you are actually compressing something else that is mixed in with the solid. So some of the classic examples are styrofoam, cheese. Think of another solid that you think you can compress. Marshmallows. In all of those cases, you're compressing a gas or usually a gas. In some cases, you're getting tiny compression on a liquid that's embedded within the solid. So there are spaces or pockets within the solid, and you can compress those. Has anybody ever seen a picture of a styrofoam hairdresser's head that goes deep sea diving? It's classic. So what you have here is a picture of 3 styrofoam heads that were all taken to varying, well, this first one was left on the surface. This one never made the trip. This one was taken to one depth, and this one was taken all the way down. And what happens, styrofoam is made up of small solid, amorphous solids, styrenes, that are mixed with a lot of air. There are lots of little air spaces in there. That's why they're so light or so low density. So when you take them down deep in the ocean, all those gases within the styrofoam head are compressed, and the overall outside appears to shrink, so you have a shrunken head. The solid is not being compressed. The gases that are embedded in that solid are what are being compressed. Solids and diffusion. So we talked about gas diffusion. We've talked a little bit about liquid diffusion. Do solids diffuse? Well, diffusion is, of course, the movement of molecules from areas of low concentration to high concentration due to their random motion, random Brownian motion. Can a solid diffuse? Yes. Yes, it can. If you clamp a piece of zinc metal and a piece of iron metal together, they will, over thousands upon thousands of years, begin to trade particles. It's going to take a really long time, but after maybe millions of years, you will start to see a few atoms, like seriously, individual atoms, not even enough that you would notice it, of one in the other. So you'll start to see some little atoms right at the surface at the interface actually diffuse and switch places. It's incredibly slow. It's not so that you'd notice. We very often say that solids don't diffuse because it's so slow that it's almost not happening. We'll actually pause in our notes here today, and we're going to look at some of the crystals that Steph brought in and look a little bit at shape and structure. We'll do a little bit more with crystal shape and structure tomorrow. It's something that we normally don't go into in any kind of great depth, but we will because of the upcoming Carnegie trip. So we'll stop notes there today, and I'll give you your homework assignment so that you can work on that in 5C. Questions, comments, concerns?